of a representative of the hard exterior with the soft middle on the inside. For this particular test, we are going and testing standard orthopedic drills that are used in surgery now versus what a metal manufacturer could provide us to kind of like match against the different levels of knowledge that were being used. And the issue that we're trying to cover here is that we've noticed that there's a big gap in knowledge on drilling technology between medical uses and metal manufacturing. And we want to kind of narrow that gap down so that there is a higher chance that a surgery will go successfully and less trauma for the patient if you're using a better drill. And here we can see the medical clamps. On the left is the original clamp that I was basing my model off of. And what we were trying to do is kind of match it as closely with making some minor changes to improve the functionality.
We're not seeing the slides.
Yeah, Trent, the slides are not advancing.
Yeah.
They're not advancing.
You need to share a different screen.
Okay.
Sorry, folks, we just realized that.
Yeah, technical difficulties.
If you go to slideshow mode from right there.
Yeah, that's what I did, but
You could see the slides, but they weren't moving?
Yeah, we're just seeing the first slide.
There we can see the proper slide. There we go.
Hold on.
I got the product here.
Hit the buttons, the three dots,
Okay.
and hide presenter view. You should see it now.
Okay, there we go.
Do you see it?
Okay, that looks good.
Nope,
Thank
you're
you.
good.
Thank you.
So here are the two blocks that I was speaking about when you couldn't see it, unfortunately. And on the left there is a foam that's representative of the inside of the bone. And then on the right is kind of representative epoxy of the hard exterior of the bone. And then I'll get into the medical clamps. On the left is the original clamp design that I was copying off of. In the middle, we can see a plastic prototype that there are minor changes to design to either A, make it easier to assemble, or B, increase functionality of the clamps. And on the right is the final titanium print that we made to test out how strong these metal 3D prints were and if they could be used for medical clamps. And the big change that you can see is that down by the handles, there's a swinging arm where the teeth ratchet so that while in surgery, the surgeon can go and clamp down on something and it stays clamped down and they don't have to worry about it. But the issue is with the original design that clamp doesn't start until you're already pretty closed on the clamp, and a lot of times bones end up being much thicker than that would allow. So they couldn't get clamped soon enough, so they had to work around the limitations of their tools. But now you have the potential to make a new clamp that it can better suit them in surgery and allow surgeries to go faster. And for the drill wear analysis, I was going and taking pictures of 4 different drills, running them through the 2 different materials. And I was taking pictures every so often and analyzing the wear throughout the test and then comparing them to the other drills that we were testing, and then also comparisons within the different tests of each drill. And this was a very exciting project because I got to find out lots of just like industry knowledge where you're analyzing drill wear, so then you can go and see what would be the best tool for the job, as well as getting very familiar with using a microscope and application here at OMIC, where a lot of our research projects require this kind of work. We are analyzing how things are being used throughout the project. And then there were some minor projects that I did along the way, such as getting certified in our manual machines here, where I made a hammer scene below. And I also did 3D printer repair, fixing the printer here and just making sure we could get it back up and running and working as best as we can. And big things that I've learned are the science of machining, because Hermes taught a class to us all about machining solutions, where we got to learn why you would do something in machining instead of just being told this is how you do it, because it's so much more valuable to know how to make the decision yourself instead of just referencing something that tells you what you should be doing, because not every situation calls for something that has already been laid out. And I also, once again, learned how to use the manual machines and really got refreshed back up on those and got to get up to shape on learning how to use them because it's really valuable to have those basic skills. Then when you start applying it to the CNC machines, you know what's going on. So one of the big next steps I took was actually learning how to use our Akuma CNC mill for the drilling project so that we could get very controlled, precise drills repeatably between all the different tests. And for that test, I also did manual NC programming, which is what the machines understand. And I did that all because the drill program itself is very complicated, but it just, not complicated, it's actually very simple, but it just requires a lot of inputs to make sure we're doing everything correctly. And a big skill I learned was microscopy for tool wear analysis, where I got to measure all these drills throughout the whole operation of the test. And some final thoughts that I have is I really enjoyed the freedom in projects because once we were given something that we were supposed to be doing, if we needed help, we had the ability to go and ask the researcher we were assigned to for help, but we weren't constantly being watched over and we could really take the lead in what we were doing. And being allowed to like take a lead in this research is so valuable because now I know for a fact that I understand what we were doing instead of just following along because I was the one leading this part of the research and getting to learn along the way. And in the future, I would love to be trained on more equipment so I could better assist in research done here at OMIC. And I also believe that a big thing that we could do is performing research on topics that the interns are seeing as needing research done because not every topic can be seen by industry members and sometimes you just need that fresh eye. So next, I'm going to be passing it off to our next presenter.
Thanks, Trent. Hello, everybody. My name is Jacob Falk. I'm actually from the St. Helens, Columbia City area down the road from OMIC. I go to the Wilsonville campus, Oregon Tech, as a manufacturing and engineering tech. I'll be going into my junior year, and my assigned researcher for this summer was Josh. And pretty much the first day that we got here, we got assigned some research projects, and mine was comparing scanner technology to CMMs. So on the left there, that's a CMM. It uses a probe and it physically touches your part to measure the part. And on the right is a scanner, and that's using optical technology. So it could be blue light, it could be lasers, it could be a camera, but the bottom line is that it's not touching the part, it's using optics to scan your part and to create a part in 3D space. And we're going to compare these, so one might be faster, one might be more accurate, and we're going to compile these and find the pros and cons. And one part of that is we're going to test multiple different scanner technologies to find the best one, and then we'll also be comparing that to the CMM we have here already at OMIC. So part of my job was to find different scanner companies, to find different products, to see what companies have to offer so that we can compare all of them. Another element of this project is getting trained up on GD&T, which is geometric dimensioning and tolerancing. It's basically the language behind parts. So from design to production to inspection, you use GD&T, and this lets everybody speak the same language throughout the whole process. And if you're fluent in GD&T, then everybody can be on the same page, and it makes production cheaper and it makes everything run easier. So part of that with measuring these parts and comparing them from the CMM to the scanners, I would need to be, have this in my repertoire. So OMIC actually purchased an online training course with hours of video just to get people trained up on this. And I'm just going to give a basic example of GD&T so that I can kind of put it into context. So this is just a basic example of a mirror. And typically you'll see just dimensional callouts. So it needs to be this wide and this thick, and that's it. GD&T adds another layer on top of this. So if you wanted the mirror to be flat and not have a curve in it, you could just say, I want it to be 0.1 millimeter plus or minus 0.1. But then what you're doing is you're telling the manufacturers they can't have very much deviation in the thickness. You're saying you can only go 0.1 millimeter, and that's going to make the part really expensive. So instead what you can do is just do a simple flatness call out saying the mirror needs to be flat. It doesn't necessarily need to be exactly the same thickness all the way through. So then you're allowed to bring up your thickness to 0.5 millimeter plus or minus, and then this basically just lets everybody know the design intent. It lets everybody know what the part is going to be used for and what the best callouts are going to be to make it be produced the easiest and inspected the easiest and designed correctly. And then I think this is the last aspect of this project is being able to program the CMM. With scanners, you can set the scanner in front of a part, move it around the part, and it scans your part. But with the CMM, you have to program it and tell it, this is where you're gonna go, this is the feature you're gonna measure, and you have to set it up so that it's outputting all your data. And so it's a little bit more, there's a much steeper learning curve than a scanner. So part of that was being trained on programming it, and I'm still doing that, continuing, learning how to use the CMM. On the right, there's just a screenshot of the code that the CMM runs through. And on the left is the CMM head, and that's a chainsaw bar right there in the picture. Another major part of this summer internship was being able to participate in a cutting solutions training with our maze. This is a screenshot of his book. Basically, we met once a week and we learned all about cutting technology, feeds, speeds, and how everything related. I didn't realize how much everything is related on the right there. All those parameters go into equations and it all goes up the line all the way to horsepower and material factors. And I just didn't realize how much everything is related for the parameters of cutting. And this was really useful because this isn't something you learn in a college class. Like I'm a manufacturing major and we don't have a class that's specifically dedicated to cutting technology. So this was kind of an insider scoop to get more detailed information on the topic, which I really appreciated. Another part was Zoller tool training here at OMIC. So a couple week ago, we got training from DeArmond from Zoller, and he took us through the software of the tool storage system. And it's a pretty complicated software. It's not just, okay, here's your tool, put it in, you're done. There's a lot that goes into it. So we got to take a couple days with him, and he trained us on how to enter in tools, how to create them into assemblies, how to create CAD models in the software that then goes back to your machining program so that you can simulate your machine with tools that you have already out in the shop. And it was really cool to see that all come together. And then the next stage of this is going to be to create a training video for future OMIC staff on how to use this tool storage. That way it can be referenced later on down the line. So here's another project I helped out with, and it was creating microscopy prints, so 3D prints. And then this next picture, I'll kind of show you the application. So on the left image there, you can see that there's a white card that's sitting just below the cutting tool, and that's just reflecting light back up on the tool. The vise down there that's holding the tool, that was just something we found on Thingiverse, just a 3D model platform. It was free, we grabbed it, we printed it. And this shows the different image quality that you can get just from a simple tool, just from that simple reflector. So on the left there, you can see the faces, the flanks are kind of washed out on the cutting tool. And on the right, it kind of brings more detail to the cutting edges. And this just gives you more options when you're doing microscopy. The more options you have, the more different angles of light you can provide to your tool, the better you can be off. So that's one of the projects I had. And then here's another 3D print to help out with microscopy. Usually V-blocks are just 45 degrees, but I printed some out that incremented by 5 degrees. So this lets you view inserts at different angles, and that's going to change the way the light hits them and change the way you're able to see the cutting edge for microscopy and research. Just like the other interns, I took part in manual machining. So this is my personal hammer that I machined out. This is a hammer that we all did together. We all had a part in making different features of that, and has a little internal storage pocket. This was kind of like to showcase the manual machining course that we did here. And then another project I took on was creating documentation for that manual machining course. So they wanted to be able to pass these documents to anybody else who comes to OMIC in the future and get them signed off on manual machines. So I created a set of documents that had instructions with them. Daniel helped put all the detailed instructions for machining. And then on the right, that's the final sign-off sheet. So once they're done, they get a score, instructor comments, and all that. And then these next projects are just some small little things, kind of upkeep here around OMIC. So one of the things is the manual lathe, the feed handle just came out of the machine. It was broken, so I went ahead and took it out and re-tapped it, put it back in and fixed that. So now that's sturdy and hopefully never breaks again. And in fact, the other lathe that we have right next to it broke, so now that one's next on the chopping block. Got to fix the other handle. Another thing is helping with the surface grinder. And I just want to give some context to the surface grinder before I talk about it. Basically, a surface grinder is taking off very small amounts of material to get very precise tolerances. So at the bottom, you can see milling. That's basically roughing. And then you'll see up towards the top of the line, surface grinding is going to give you a much higher tolerance. You're taking off very little amounts of material. And every surface grinder needs to be balanced. The wheels, if you don't balance them, you're not going to get an even surface on the top of your part. So it needs to be taken off, tediously balanced. It takes a long time, a lot of patience to balance the wheel, and then put it back on, and then you dress it with a diamond stone. So now it's spinning true, and it's ready to go. And then this was some more tool cabinet organization. This is a different cabinet, a different storage system. But me, Drake, and Daniel all went through about 450 tools. That's an estimate, and just entering all of those into the storage cabinet. Everything from inserts to like 12-inch long cutters. Another small project is the bench grinder. We got this bench grinder here, we got it mounted, and then it had a vacuum port so you can suck dust out while you're grinding. That way the fumes aren't going up into the air and the dust isn't getting all over the white floor. So I 3D printed that white piece. You can see it a little bit on the right picture, in the middle of the picture. There's a white piece that adapts down to the vacuum cleaner. And then on the right here, or on the left here, this electrical receptacle, what it does is it turns on the vacuum cleaner once you turn on the grinder. And then once you turn off the grinder, the vacuum automatically turns off. So it was like $30 off Amazon. It just adds a little touch of automation that makes it easier for the user and safer too, because you don't have to bend down and manually turn on the vacuum cleaner every single time you want to use the grinder. And that's all I have for my participation during the summer. Going forward, I'm looking at being part-time here at OMIC for fall employment because I'm going to the Wilsonville campus, so I'll have extra time to help out here with that research project with the scanner and CMM. That's going to be a longer-term project that I'll be able to help out with here. And then I'll be focused on GD&T and more programming the CMM because that's not a small task. It's going to take a lot more learning and practice. And then overall, I'm very content with the skills I learned this summer. It was a great experience, and I'm looking forward to being able to apply everything I learned this summer to my classes and also to whatever future prospects I have. And that's all I have for you guys today. So who's next?
Daniel.
Daniel Delancey.
Sweet, thank you.
Yep.
Hello everybody, I'm Daniel Delancey. I'm a junior in mechanical engineering in Klamath Falls at Oregon Tech. I come from a small town in northeastern Oregon called Wallowa, and my assigned OMIC staff member here at OMIC was Cody Apple, and my focus was on learning CNC programming and machining operations. One of the first things that I noticed coming here to OMIC was, so this is the OMIC project reporting template, and I actually made a video of how this works. I actually made a program within this reporting system, and I made these little buttons that you can add various tasks into the system, and it'll automatically color code the 6-block chart. And this is really useful because previously how the researchers were reporting their project progress was by hand. They would fill in these boxes manually and change the colors of the boxes, as I said, manually. And when I saw that, I thought, well, maybe I could write a little basic program that makes it easier to use and it makes those colors happen automatically rather than inputting it by hand. And I made these little user forms, and you can click buttons, and it's super user-friendly and easy to figure out. So there's an add task button, an edit task button, and a delete task button. And the video is moving kind of fast, but as you can see, it based on the status of the project or of the task, it in the top right changes the status of the entire project. So if it's like a red status project or task, that's like the worst status it can be, and it'll change the status of the entire project to red. Or green. So later on here, I decided to take the CSWA exam to get certified in Dassault Systems SolidWorks software. So I passed the exam and I got an associate level certificate in mechanical design. So that was good. And later on, one of the projects that was presented to OMIC was to test binderless CBN, binderless cubic boron nitride, which is a cutting tool technology. And they wanted to get this specific kind of insert certified for cutting aerospace grade material at a high rate of speed and see how well the tool would last, tool life and longevity of the tool. But an issue we ran into is we did not have a file so we could program the part to be turned in the machine. So we had to manually measure the part that they gave us because they gave us a bad part. So what we did is we took these precision measuring tools, and myself and Drake got to get experience using this precise measuring equipment. And we measured this aerospace part. And then once we measured that part to a high tolerance, we remade the part in SolidWorks, as you can see in the top left. That's the SolidWorks file. And then with Cody Apple, we went through with that file and we made a program for the WFL mill turn in CATIA, and we were able to prove that that cutting technology could turn that material at a higher speed and achieve better surface finishes than the technology that was being previously used. So that was a great accomplishment for OMIC, and I felt myself and Drake as interns. It was great for us to be able to participate in that. As the other interns mentioned, we got a certification using the manual machine equipment, and we made brass hammers. So on the left is the personal hammer that myself made, and on the right are the two hammers that we made as display items for OMIC to stay here while we're gone. This was a part that came in a few weeks ago. A professor who's actually here in the Zoom meeting, Professor Xing Yi, requested this part to be made for his load testing. So that project was given to Drake and I as interns, and we were able to meet all the tolerances, and it worked out great. So I was happy to be able to help out with that. And a few weeks ago, I came into a period of time where I wasn't working on any projects in particular. So personally, I wanted to familiarize myself with the ACU-RITE mill programming interface. So what I did is I programmed this little cutout at the end of this peg that you see. I programmed that in the mill, and these are actually pegs for my motorcycle, and they fit perfectly and everything worked out great. And I was able to teach myself to use the ACU-RITE programming interface. So that was good. I've also been working on familiarizing myself with CAM software. And right now I'm using a program called Streaming Teacher to learn Mastercam. And I've been using that for the last few days. I haven't made substantial progress on learning CAM software, but we are working on it. So what I've learned here so far is basic CNC practices and setup. I've helped set up the WFL machine and the 5th axis for a few projects. And then I'm learning CAM principles and manual machining processes, precision measuring and meeting tolerances, and machining solutions with Hermes Narwala. As you guys have heard, we've been taking classes with Hermes, and he's been an extreme help in helping us understand the science behind machining and cutting metals and all that. So that's been incredible. And my plans for the future here at OMIC is I would like to become completely proficient in using CAM software and CNC programming. And I would like to begin using CNC machines and learn CNC operation and procedures. And on that, I would like to pass it to our final presenter, Drake Juneman.
Cool, thank you. Thank you very much. So first and foremost, I'd like to thank everybody for joining the call, specifically extending the thanks to the DeArmond representatives that are here today. So it's been a very cool opportunity for us to be a part of this internship. So my name is Drake Juneman. I am a junior in the Mechanical Engineering Technology program. I am from North Plains here, about 45 minutes away. And my assigned staff member from OMIC was Cody Apple. He's been great to work with. So one of the main overarching projects that we did throughout this summer was getting certified on the manual machines, as the other interns have mentioned. And that project consisted of making brass hammers. So here is mine that you can see, adding my own customization to it in the form of grooves that are blue. And it actually turned out pretty good. And the context of doing this was to get certified on the manual machines before stepping up to the CNC machines that are here. So we learned how to cut threads on the manual machines. We learned how to turn, how to face, how to do all the basic operations, including the safety. And I had taken 4 years of machine welding fabrication in high school, but this was a great way for me and the other interns to expand their ability on how to use these machines. So here's kind of all of our hammers, a couple pictures of them all put together with the different designs we came up with. And then these hammers are the ones that were sort of a collaborative effort between all of us. So on the hammer on the far right over there, I made the handle, Daniel made the head, and we all kind of contributed our own little touches there. These will be displayed in a sort of shadow box in the hallways of OMIC here, hopefully soon. So, as Daniel mentioned, I participated in the titanium turning project that we did here for OMIC, where we tested binderless CBN inserts, or cubic boron nitride. And this insert was made to test turning titanium and to test the longevity of it, as well as increase the feed. And it actually, the results produced pretty good results. We were able to run the insert for much longer, and it was a very fun project to participate in with Daniel and Cody. So along with that, we had to recreate the part using precision measuring tools. So these are just some of the ones we used: internal bore gauges, micrometers, big calipers, things like that. We actually were able to recreate the part in modeling software, which then got into the software for the machine. We ran the part, simulated it, and then once we tested it, we came up with the final results there. So another project that I participated in with Jacob and Daniel was organizing the tool cabinets here at OMIC, because there was a lot of tools, but they weren't inventoried and they weren't organized in the best way. So we took this project on of learning how this system worked and organizing every tool, like Jacob said, from little end mills or inserts to big, 1-inch carbide end mills or something like that. So we actually organized it in the best way possible and fit as much in there as we could. And it's actually, you can definitely find any tool you're looking for there now. So another lathe project that I participated in was the load tester attachment for Professor Sung Yi. He wanted a load test attachment made out of a hardened steel, and we didn't have the capability to machine this on the CNC machines or the time to make a program for it. So Daniel and I took this on as a manual lathing project, and it had to be within a pretty tight tolerance, but we were able to pull it off, and it was a fun project for us to do because we got to use certain tools on the lathe that we hadn't used yet, such as a boring bar and some other techniques like the taper and stuff. So one of the last projects that I participated in here was learning the software for the Zoller tool cabinet. Dietmar gave us some very helpful instruction on how to use the Zoller software and the tool cabinets. And these are very good because they're organized in such a way where you can store everything from little screws and little inserts all the way up to tool assemblies. So you can individually inventory all the parts and then make an assembly and store the assembly. and then you can call it up on the machine, and it's got a lot of advanced features that are very useful for a place here like OMIC, and we got to learn how to use that over the course of 2 days from DeArmond. So some of the main overarching things that I learned throughout the course of this internship. I refreshed my ability to use the manual machines, as I said. That was a great project to work on with John Lawrence, who was the machinist here. So another thing I learned was the process of measuring, modeling, and running a part on a CNC machine. So I hadn't actually learned how that whole process worked. It was very interesting to go from a base part to measuring it, to modeling it, and then actually running it on a CNC machine. I got to see how all that kind of works. Using precision measuring tools, again, with that project, I had never used quite that high level of precision measuring tools before. So that was very interesting. I got to learn the terminology about cutting tools and machining solutions from Ramaze's class, like the other interns have mentioned. That was a great opportunity for us because we got to learn specifics on feeds and speeds and rake angles and things that I didn't even know about, and learn the science and art aspects of machining. And last but not least, I got to learn OMIC's method of organizing and reporting projects, and how they keep track of all the projects that they do and how they do the weekly reports of them every week, and that was something that intrigued me. So some of my future goals, leaving here at OMIC while going back to school for the fall, I want to become more skilled at running the CNC machines. I've been using the manuals, I've been around the CNC machines, but it would be very useful at some point to expand my ability on how to use those. I'd like to use the knowledge in general from this internship in my classes and during school. So I'm kind of a hands-on learner, so anything I learn around here, I'd love to use that in labs at school. And whatever skills I can get my hands on and knowledge, use that as a boost for my classes during school. And I'd also like to expand in a field that intrigues me, such as automotive or aerospace, because if there's something that interests me, I always enjoy working on that specific subject. So materials in terms of automotive or aerospace, that's right up my alley. So kind of going along with using my knowledge from this internship, I want to go into a field that really, I enjoy. So I think that is it. So thank you very much again for attending. That wraps it up.
Thank you, gentlemen. Ramaze, I know you wanted to share a few words with our audience about the interns and about the work that they did over the summer. And then after that, we'll go ahead and move to any of you who may have questions for the DeArmond Fellows.
Thank you. Hello, my name is Ramaze Jairwala. I'm the head of R&D at OMIC. And a great job, guys. Thank you very much for your presentation. You know, the one thing I'll share about internships, I know several of us were there at one time, much earlier in my career. They have a curious mind, a willingness to contribute, and a fantastic work ethic. I think those are some of the best personalities and recipes for success. So great job, guys. You know, I want to continue. I want to request all of us. We want to continue to help them find their passion in this trade of ours and in industry. So please do consider opportunities to invite them for tours or visits, or even go on sales calls or a coffee talk. Let's really expose them to what's out there so they can make some good decisions. And I'm pretty sure they're going to make all of us proud, if not already. So thank you very much. I'm honored to be a steward in your internship. So, great job.
Thank you.
Thank you.
Let's go ahead and open it up if anyone happens to have any questions for our DeArmond Fellows. I know they're not shy in responding, so feel free if you have a question for them. All right, well, I'm not hearing any questions, so guys, you got off really easy. Again, wanted to thank all of you for taking the time to listen to their presentations, learn about what they've been doing here at OMIC R&D, and also to reflect what Hermé said, cogitate a little bit on if there are opportunities that you might be able to have as they continue in their educational career at Oregon Tech, that you might be able to find an opportunity for them to learn more about your business or the work that you do either in the private sector or at Oregon Tech or in research. And with that, we'll go ahead and close down our presentation for today, and thank you all very much for joining. And thank you, Mr. Tom Jack, for your willingness and the willingness of the DeArmond Foundation to provide this very valuable scholarship for these students. Hopefully, we're going to keep all of them working right here in Oregon for our manufacturers here. And with that, thank you very much. Have a great rest of your day, and take care.
Great work. Bye.
Good job, everybody.
Good job, guys.